velocity varies with the solar cycle. In fact, at a normal solar minimum, there are long-lasting fast solar wind spreading over a large equatorial large angle from both poles, and while in the equatorial plane we have a slower solar wind. At a solar maximum, the distribution of the fast solar wind should be approximately isotropic. So, in conclusion, we can say that we need a balance between physical resistivity and grid resolution to achieve convergence, and in the future I'd like to move to more realistic 3D case with more advanced technique as the guiding center approximation, because the number of points would be enormous in order to reach convergence. I also found that the resistive electric field contribution is fundamental in accelerating particles to high energy, and I would like also to insert a guide field, so a magnetic field along the z-axis, to see if the results change. And during my postdoc at the University of Arizona, I will investigate the transport of cosmic rays, and I try to model the gamma ray emission observed by Fermi. As to date, there is still no model that can fully explain the emission. Okay, that's all. Thank you for your attention, and I'm here for all your questions.
if you want to do that, but like to move slides.
Yeah. I can just go back and forth like this. It's fine.
Very good. Today we're very, very happy to have Lam Hui visiting us. I'm going to give a very brief introduction and move to be a postdoc at Fermilab and very briefly at the IAS before joining Columbia, where he's now full professor. Lam has very broad interests in astrophysics, particle physics, cosmology. He's done pioneering work in fuzzy dark matter, wave dark matter, which he'll tell us about today. And particularly this paper here, 2016, sort of kick-started the recent interest on this model. And to give you an idea of the level of interest, I checked this morning, it has had ordered 10 to the 3 citations, which I think average to 1 every other day, more or less. But Lam's also done a lot of interesting work in broadly astrophysics. He started a lot of work in photoheating of the IgM, showing the Lasker structure, both in theory and with SDSS data, and has done recently a lot of nonlinear interesting work on black holes, which we'll hear later in the ITC lecture. So without further ado, please, Lam.
Thank you, Julian. Thank you for the kind introduction. And thank you for the opportunity to speak to you. I encourage especially the students to ask me questions. Although all questions are welcome, of course. Please interrupt me. I want to spend the next hour or so telling you about some work on wave dark matter. And the work is basically listed here. If you are interested in background information, there's a review I wrote recently, which you can look at. So what do I mean by wave dark matter? So let's talk about that, right? It's intentional not to use the term fuzzy dark matter, and you will see why in a moment. I don't think we need this slide given this audience. We have a lot of astronomical evidence for the existence of dark matter, and they are all based on basically the gravitational effect thereof. And the amount of evidence is pretty overwhelming and strong. It's something that most of us are fairly confident is something that exists, although we have no idea what it is. That's the dark matter problem, right? Now, if the dark matter were a kind of particle, to illustrate our degree of ignorance, here's a spectrum of possible masses for the dark matter particle that is out there in the literature. It ranges from, in this talk, what I would call ultralight, it would be somewhere there about 10 to the minus 20 to 10 to the minus 22 electron volts. That is often referred to as fuzzy dark matter. And it ranges all the way to basically astronomical masses, right? Basically solar mass or tens of solar mass. Primordial black holes is one candidate that is often discussed. The fact that this spectrum is so immense illustrates our degree of ignorance. We really have no idea. It's interesting. We can actually put at least one scale on this plot that kind of make a distinction between two different regimes. And it comes from asking the following question. So what is the question? So first of all, we start from a data. What is the data? The data is the mass density in the solar neighborhood is around this number, 0.3 GeV per centimeter cube. If you like astronomical units, it's more like 0.01 solar mass per parsec cube. It's basically that number. It's basically based on stellar motion, right? We know that much mass density is out there. Starting from that data, we can ask the following question. At what particle mass, by the way, can you hear me okay in the back? Yeah. At what particle mass is the interparticle separation less than the Broglie wavelength of that particle? It's kind of maybe a little bit unusual question, but clearly it's a question you could ask. Right? Imagine the particle is very, very light. To make up this mass density, you must need a huge number density, right? With a huge number density, the interparticle separation will be tiny. And it could be so tiny that it's in fact even smaller than the Broglie wavelength of the particle. And to remind ourselves, the Broglie wavelength depends on the mass of the particle like so, but it also depends on velocity. And here I'm going to take the velocity dispersion of the Milky Way, something like 200 kilometers per second. Okay, so let's ask that question. At what mass would this inequality hold? And it's a simple calculation given this observed quantity. And after doing the calculation, you would find something like this. Essentially, if the particle mass is less than about 30 electron volts, which I'm going to call the wave regime, we are in a regime which is basically visualized as follows. So if you draw the Broglie sphere, the radius is the Broglie wavelength. You are in a regime where there are multiple, even many particles in that, basically the Broglie volume. So the analog, which is fairly familiar, is to think about electromagnetism. No? Suppose I tell you you have a certain state where you have lots and lots of photons. In that case, as we all know, it's helpful to actually just think of this as electromagnetic waves. You open up Jackson, and we know everything about it. We know how to do calculations, make predictions. This is the wave regime I'm talking about. Basically, exactly the same, except that here we're talking about dark matter particles as opposed to photons. I should also say, by assumption, just having multiple occupancy in the Broglie volume means these particles, whatever they are, they have to be bosons. They cannot be fermions. If they are fermions, you cannot actually shove more than one particle per state, as you know. So this is some kind of bosonic particle. For this talk, I'll mostly use a spin zero particle as illustration, although much of the wave phenomenology would apply regardless of whether the spin is spin 1 or even spin 2. Okay? Spin 0 is what I'm going to stick with for the most part. And to give you a sense of scale, let's talk about scale, right? So suppose the particle mass is around this threshold, let's say 10 electron volts. You can plug in numbers. The de Broglie wavelength using 200 kilometers per second for the typical velocity. The de Broglie wavelength is small, like so. As you dial the mass down, then it's obvious the scale has to become large. And for ultralight masses, which is the fuzzy dark matter regime, the wavelength becomes so large that they are sizable. It's a sizable fraction of a galaxy. And obviously, there will be lots of astrophysical implications. I put down 10 to the minus 6 electron volt because this is the target mass of some prominent axion detection experiments. For example, a microwave cavity experiment known as ADMX. That is the target mass, 10 to the minus 6 electron volts. If you convert into the Broglie wavelength, it's not, the wave effects are actually important for these experiments. That's actually what I want to spend some time talking about. So this scale, which is some fraction of a kilometer, is larger than the size of the experiment. And it has implications for how you should think about dark matter detection in those cases. So that's what I want to talk about. So in this talk, mostly I want to focus on wave phenomenology and dynamics, more or less independent of what the mass is. What I'm going to say is fairly generic. It doesn't matter whether it's ultralight or not. However, of course, the observational implications are going to be more easily detectable, more pronounced in terms of astrophysics, the lighter the mass is, right? Okay, so we'll for sure talk about that as well. Okay, so that's the setup. This is what I mean by wave dark matter. And in this talk, when I say fuzzy, basically think of ultralight. But if I use the term wave, basically anything like this, in this less than 30 electron volts is wave dark matter. Okay. So here is the outline. No? So the outline is I want to spend perhaps maybe 10 minutes just telling you why we should even think about such a light particle as a dark matter candidate. There are actually some good particle physics motivations. So I'll review that a little bit. By the way, 10 to the minus 6 electron volt, that's the QCD axion. That's the target mass of ADMX experiments, although QCD axion actually has a pretty big range in mass also. And then the bulk of the talk is actually just reminding ourselves what are the kind of basics of wave dynamics and phenomenology. Okay? And then I hope to have time to talk about the astrophysical implications, especially if you are at the ultralight end of the spectrum. But I also want to spend some time talking about what does it all mean for experimental detection if the dark matter is merely light, not ultralight necessarily. So that I will talk about as well. And of course, I should acknowledge, the term fuzzy dark matter was coined by our friends listed here. Let me pause in case there are questions before I launch onto the first topic. No? Okay. Please do feel free to interrupt me. Let's see. Particle physics motivation. I'll be fairly brief here. So if I tell you, look, I have a particle that is very light. A very natural thought would be, well, it's probably close to being a Goldstone boson. As you know, if you have an exact Goldstone boson, it really should be just massless. But in fact, very often what happens in particle physics is non-perturbative effects often can actually give such a Goldstone boson a small mass. So hence the name pseudo-Goldstone boson or pseudo-Nambu Goldstone boson. So that's basically the zero-order thought, that, okay, a light particle may be a good candidate. It's a pseudo-Nambu Goldstone boson. And this picture is meant to kind of remind ourselves roughly how it works now. So phi in my talk is going to represent that boson, right, that light particle. And it's like a Goldstone in the following sense. If you draw a potential, you have basically a two-dimensional potential, the usual Mexican hat potential. If this potential were not tilted at all, we are going to tilt it a little bit in a moment. If it's not, then you really have a U1 symmetry rotation around. If your vacuum were, because the potential has this form, the vacuum are actually down here, along this circle down here. And the excitations along basically this direction is the Goldstone boson. Because the potential is flat, that is a flat direction, so you have massless particles. So that's the idea of the Goldstone boson. Again, non-perturbative effects often would take this potential, you can imagine, visualize, and tilt it a little bit. And that tilt comes from, for example, instantons. They are generally very suppressed in the sense that they are kind of the analog of what we are familiar with in quantum tunneling. So the probability, as you know, is exponentially suppressed in quantum tunneling. Likewise, in these cases, the mass that you would generate for the Goldstone boson is also exponentially suppressed. And so you get something that's naturally light. Of course, the most well-known example, I should say, is the QCD axion. Is most well-known because it's motivated by a completely different problem, the strong CP problem, which I'm not going to talk about. Mainly, it has to do with the observational fact that the neutron dipole moment is very constrained, and this is basically an attempt to explain that. And the outcome of that discussion, which actually involved a lot of these people here, is that this turns out to be an interesting dark matter candidate as well. So because of that kind of separate motivation for the QCD axions, a lot of people find this a compelling candidate, and therefore experiments have been built and will be built to actually look for this QCD axion. Now, I should say, more generally, there are a lot of axion-like particles. So often the term axion is strictly used for just the QCD axion, although that's not a universal terminology. If you want to be precise, there are a lot of not quite QCD axion, but axion-like particles, meaning they are basically can be visualized as something like this. They arise in string theory, where you have, if you have extra dimensions that's compactified, these axion-like particles arise as basically Kaluza-Klein zero modes of higher form fields. And if you believe that story, there are lots and lots of such particles in principle. And so there are nice papers written about that as well. What I want to say before we leave particle physics motivation is one particular story is kind of a footnote that has to do with fuzzy dark matter, the ultralight version. So it turns out the ultralight version, there is some kind of nice numerology that somehow work out. So let me show you that argument. So by ultralight, once again, I mean something like 10 to the minus 22. Although, as you will see, once you follow this argument, you will see there's actually a rather large range, actually, even in this story, okay? But let me tell you that story, right? So what are we talking about? We have an axion. If I ignore non-perturbative effects that tilt the potential, it should be strictly massless, phi. So you will have the usual kinetic term in the Lagrangian, and that would be it. There would be no mass term, no potential. However, as I try to explain, perhaps not very well, because of non-perturbative effects, there's usually exponentially suppressed potential, and it would take this kind of form. The fact that it has this funny cosine is basically because this phi is really like an angle, because you go around like this. And so you have some kind of periodicity. But you generate a potential set by this scale. This lambda is going to be some very small number. Again, motivated by the thinking that this arises due to something that is analogous to, let's say, the way you compute quantum tunneling, exponentially suppressed. Now, what are the scales that I'm talking about here? This phi is an energy scale, and so I have to tell you, if you rotate phi by some amount in energy units, then what is the periodicity, right? I have to tell you. And this capital F is supposed to be that periodicity. In other words, is really phi over f. That's the dimensionless angle, if you want. Okay, it's that angle. If you expand around basically small phi, you can convince yourself you would get a quadratic term. From the quadratic term in phi, you can read off the mass of phi, m squared phi squared. Just Taylor expand basically this cosine. And you can convince yourself that m must be related to f and lambda in this particular way. And once again, lambda, think of lambda as basically this fundamental scale f, but exponentially suppressed. And therefore, your m, the mass that you get out, would be very, very small. So that's kind of the idea, the basic idea. Okay, so that's the construction. Now let me tell you the numerology. The numerology comes from thinking about radic abundance. So this mechanism for producing some significant amount after Big Bang is known as the misalignment mechanism. And misalignment in the following sense. So here I sketch out the potential. This is the potential. So this V of phi, that's the potential. And once again, there is some scale. So the x-axis here is phi. The y-axis is the potential. And this stretch is supposed to illustrate basically the periodicity scale. It's basically 2 pi f here. Okay? As phi go from this point to that point, this phi basically go around like that. Yeah. And what do we mean by misalignment? So this is kind of the first assumption in the tale, if you want. The story goes that let's suppose this scalar field in the early universe was not sitting at the bottom. It's sitting actually somewhere here, which is not completely crazy if you think about it, because this potential, even though I draw it like this, is extremely flat, right? This lambda is very small. So it's almost like a flat potential. And so the assumption is, well, there's no particular preference for this field phi. And so let's just assume, using the only dimension you have in the problem, which is basically this energy scale f, let's assume phi over f is order 1. Yeah? So the fact that phi over 1 f, this angle is not 0 but order 1, that's why people call it misalignment. Okay, so imagine this scalar field has this primordial value. Now that scalar field for a long time would not do very much at all because of Hubble friction. The universe was expanding very fast. The Hubble friction basically kept the scalar field basically stuck at whatever this primordial value is. And it stuck there for a long time until when the Hubble expansion rate dropped enough so that it is of the order of the mass scale, this tiny mass, which is basically the curvature, if you want, of the potential. Then Hubble friction is weak enough that the scalar field now can actually roll down and commence oscillations. So that's basically the story. Once you have scalar field that oscillate like this, Hubble expansion is going to take energy out of these oscillations, and the oscillation amplitude is going to get smaller and smaller, and the scalar field will just be oscillating closer and closer to the bottom, which means for a lot of applications, you can even forget about this cosine potential. It's really just m squared phi squared potential. And you can convince yourself, once you have that, the redshifting of the energy density contained in these oscillations redshift precisely like pressureless matter. And it's something that you can show, and which means this is now a good dark matter candidate. So I want to emphasize this story is kind of fun in the sense that early on, when the scalar field was stuck here, it's not even dark matter. In fact, it's best to think of it as some kind of dark energy, right? It's staying up here. But once it actually starts oscillating like this, now you have dark matter. And if you actually follow this whole story, again, assumption is the initial phi over f is order 1, and then it starts rolling when Hubble reaches the mass scale. Then you can actually compute what is the radic abundance. You get basically the following results, that omega in this kind of matter this light boson, is of the order of what you need for dark matter, provided you make certain assumptions and choose these numbers. So you choose F. We don't really know what F should be, but if you believe our string theory friends, they have, at least in a lot of constructions, it appears F is actually can be pretty big, somewhere between gut and Planck scale. So you pick a number out of the hat, 10 to the 17 GeV. Once you choose that, in order to actually match the dark matter abundance that we observe, you have to choose a very small mass for the particle, which is basically this fuzzy-like mass, basically. Okay, so this is the numerology, but as I want to emphasize, this is really just numerology in the sense that clearly, if you look at this expression, the radial abundance is more sensitive to what you assume about F than what you assume about M. And therefore, since this F, by the way, is often called the axion decay constant, because this scale is basically fairly uncertain. We don't really know. It could go from, let's say, 10 to the 12 to 10 to the 17, not Planck scale. You don't want to reach Planck scale, but since there's such a large range, the mass, even if you believe this story, the mass that you need can have a very wide range. In fact, you don't even have to change F a whole lot, change it by a factor of a few. Already M has to change by a lot in order to get the right dark matter abundance. So one should definitely keep this in mind, right? Meaning is one of the message that I want to leave you with. Fuzzy dark matter, the canonical number is 10 to the minus 22 electron volts. But at least as far as this argument is concerned, this number is merely suggestive. Don't obsess too much about whether it has to be precisely this number. In fact, it can have a rather large range. Questions before I move on? Yeah.
If you really have a cosine potential, do you also have a phi to the fourth term with self-interaction that you have to worry about?
Yeah, if you keep expanding, so that's the m squared phi squared I thought about. Of course, there's the lambda phi to the fourth. That coupling, which is dimensionless, you can check is actually m squared over f squared. So it's very small, but in which it's actually, maybe we'll have time to talk about that as well. But it appears if you choose this kind of numbers, let's say, then that quartic coupling is sufficiently small that for structure formation, mostly it can be ignored. There would be cases where you have a lot of accumulation around black holes and so forth where you might want to worry about it. Yeah. Okay. So this is that story, but let me also end with this footnote, right? And this, for those of you who are interested in inflation, for this story actually to work, there is one assumption you have to make. Because this is this scalar is actually very light. It's very light. It's like a spectator field during inflation. So during inflation, in addition to the usual adiabatic quantum fluctuations, this field would have its own separate, what we would call isocurvature fluctuations. And observationally, they are bounds on isocurvature, fraction of isocurvature fluctuations. And in order not to violate that bound, the simplest thing to do is to postulate the quantum fluctuations in phi must be small. And the simplest way to achieve that is to postulate the energy scale of inflation is small. Okay, so this at least the simplest version of this, you actually need to just assume the scale of inflation is small. In fact, so small that the tensor modes would be hard to observe. That should be kept in mind as also. If you want, that actually is one way to test this kind of idea. Okay. Any questions? Okay. So that's particle physics motivation. I've used up half of my time. Let's talk about the dynamics. No? The dynamics is very simple, right? As I told you, because of redshifting, the particle, the phi is just oscillating. So the equation that you need to solve is very simple. is the Klein-Gordon equation that we love. Basically, looks like so. M is the mass scale of the axion or the Goldstone boson, if you want. Just discussed. We are typically interested in the non-relativistic limit because, for example, the velocity of particles in the Milky Way is not relativistic. No, it's 100 kilometers per second or so. So the standard thing to do, the textbook thing to do, is to say, well, this phi, which is a real scalar field, you can rewrite it as follows. You introduce this complex scalar field we call psi, often called the wave function, confusingly. You factor out the primary time dependence. Because if you look at this equation, clearly phi is going to oscillate with frequency m to 0 order. So you factor that out, and then you make the following postulate. You postulate whatever time dependence this complex scalar has must be slow compared to this scale set by m. So m is the rapid oscillations. And then psi, it has time derivatives, but let's assume the time derivatives are suppressed relative to m, basically. Basically, it's this kind of approximation that I'm trying to write here. So if you basically, it's this kind of approximation that I'm trying to write here. So if you make that approximation and plug into Klein-Gordon, again, it's a textbook thing to do, you get the Schrödinger equation. Hence the name, the wave function. Psi is often called the wave function. What is this doing here? This is the gravitational potential. So what I'm assuming is that whatever this particle has, the only interaction that is important to us for structure formation is gravitational. And so when you compute this box, you should allow for the fact that your background geometry is weakly curved by gravity. And so in the Newtonian regime, it's basically described by the gravitational potential. And this gravitational is really just the familiar gravitational potential, basically determined by the Poisson equation, sourced by the density. And the density is nothing other than what you would naively guess. It must be the mass of the particle times the wave function square. Think of the wave function square as the number density of these particles. Okay, that's it. You have this equation together with the Schrödinger equation. You have everything you need. If you give me initial conditions, you can solve it and look for evolution. Yeah. Here is often a source of confusion because, look, you have this Schrödinger equation. So isn't this quantum, and so on. So there's a lot of confusion in the literature. In fact, Mark, who is here, has written papers about that, trying to clear up that confusion. But essentially, the way I think probably the most helpful way to think about this is this psi, even though it looks like the wave function for sure, is really just a classical scalar field that happens to be complex. Much like in E&M, if you have a situation where you have high occupancy, large number of photons, you are going to use the electric field to describe what's going on. The psi here plays basically the same role. It's a classical scalar field. There is h bar. The h bar that is hidden here that I conveniently try to hide here. The h bar, the only role of the h bar is to tell you how to convert m into a length scale. So that's the only role of h bar. But otherwise, the way you would solve this equation is really provide initial condition for psi, and then you just solve it. Okay, so that's the idea. Questions about this? Let me give you an alternative viewpoint, which is also helpful to think about this system, because it may be somewhat unfamiliar. It's helpful to think about it as think about it as a fluid. The way you do is the following. This complex wave function has an amplitude and a phase, which I call theta. Now, what is the amplitude? Well, the amplitude must be related to the square root of the density, because as you can imagine, the mass density is really just the mass of the particle times psi squared. And so the amplitude is just square root of rho, the mass density. As a fluid, what is the meaning of the phase? It turns out you can convince yourself that phase is in fact a velocity potential. Meaning, if you look at Schrödinger equation, as we all know, in quantum mechanics, there is probability conservation, basically because there's a U1 symmetry. And that probability conservation in the fluid picture is actually exactly the same as just mass conservation, written like so, where rho times v, if you want to think about the quantum mechanics analogy, is the probability flux. And it turns out v is actually the gradient of the phase. So as a fluid, you can think about this theta as the velocity potential. The Schrödinger equation must have two independent equations because psi is complex. And so in addition to mass is another equation that looks very much like Euler equation that we know and love, where the acceleration of a fluid element, there are two terms given by the gradient of gravitational potential as expected, and then there's this unusual looking term, which unhelpfully is often called quantum pressure, even though what is really going on is neither quantum nor pressure, but it's called that way anyway. In fact, if you work out actually what this is, it's actually some kind of non-trivial stress. There's a stress tensor that's off-diagonal components. It's not really pressure. So this is basically the system. And why do I want to emphasize this way of thinking about basically the wave dynamics? Let's take the large mass limit. No? Imagine m is very big. Well, m being very big doesn't really affect this equation. Mass conservation always has to hold. But m being very big could mean actually this term is always has to hold. But m being very big could mean actually this term is negligible compared to gravity. And in that limit, you recover what you already are familiar with. It's just pressureless cold dark matter. No? The only acceleration is gravity. This term is gone. So this way of rewriting is helpful that way in addition to other insights. Any questions?
When you say m being very big, is that relative to that gradient of theta, or is that like?
Yeah, totally. You have to the only fair comparison is to actually compare the size of this term with that term and ask, well, when is this small? Yeah. And it turns out, roughly speaking, you can do the following. You compare let's remove this gradient because there's also a gradient here, so let's forget about that. You compare Gm over R, which is the potential here, against what? Against dimensionally is 1 over m squared and another length scale square downstairs. The square root rho, roughly speaking, just let's forget about that. Dimensional analysis. You are just comparing gravitational potential versus 1 over m squared, a length scale square. And so depending on the length scale you are interested in, especially if you are interested in large scale, you are going to kill off this term and you'll be done by this term. However, if you go to very small scale, at some point, whatever m you choose, this term will become important. And it's fairly intuitive because once you approach the de Broglie wavelength, you can imagine, okay, there are probably wave effects. Yeah, that's basically what's going on.
Okay, thank you.
Yeah. Other questions? Okay. Yeah, there's this whole discussion of classical versus quantum. In fact, you can find it in Feynman. Of course, there is a long history of people discussing scalar field as dark matter. I should mention that. Now, the wave effects, the wave phenomenology, or the implication for observation, a lot of them has to do with wave interference. So that's what this picture is supposed to show. Yeah, and in fact, let me just play the movie for you. Even though I call it movie, this is not a movie in time. This is just solving that system of equations with cosmological initial conditions in an expanding universe. And then you get a box, a simulation box at late times, and I'm just showing you kind of a compilation of the slices across the box. And the reason I want to show you that way, because I want to just make it, probably is obvious even just look at one snapshot that there is wave interference now, that you can see interference fringes. And it's an unavoidable feature of the fact that you have wave dark matter. And once again, let me emphasize, as long as your wave your dark matter particle has mass less than 30 electron volts, if you are able to zoom in and work out the prediction precisely, it will look something like this. It's going to have these features. You have basically interference fringes along filaments, inside halos. And why does that happen? Well, it's very simple. So let's think about the wave function now. Imagine I have host of particle orbits with random phases if it's a well-mixed halo. Yeah? So the stars and the dark matter particles, they would basically zoom around, executing their orbits inside the halo. Well, for waves, it's similar, except that don't think in terms of particles, think in terms of basically eigenmodes. So these psi n are basically the, if you want, the energy eigenmodes in that basically gravitational potential of the halo. Each of these modes has its own phase, and if it's well mixed, it's going to be fairly random. And if you sum over all these waves, superimpose them in some way, you would get your whole dark matter halo. Just like when you superimpose stellar orbits or dark matter orbits, add them up, you get your dark matter halo. This is just exactly the same idea, but done with waves. And now, if you want to figure out the density that this predicts, you have to square this. And when you square, of course, there are cross terms between different eigenmodes. They have random phases, more or less, and therefore you have interference. It's unavoidable. You must have it. And the size scale is very predictable. The typical fringe size is the de Broglie wavelength. It's basically the only scale that you have. Yeah?
This is still without the self-interaction.
This is without the self-interaction. With self-interaction, of course, the long-term evolution is going to be different. But nonetheless, the fact that you are going to have a halo that is made up of something like this, and when you square, you are going to have interference, that will remain true. Yeah, it's pretty hard to avoid. Yeah.
Do I see that it's a de Broglie wavelength from the energy
Eigenvalues?
Yeah, that's right.
Okay.
So you can basically work out from the energy eigenvalue, and the energy eigenvalue basically is determined by basically the depth of the potential, and in the end you can ultimately relate to the de Broglie wavelength. You will find typical blobs.
So different halos will actually have different fringes because they have different depths.
Because different halos have different velocity dispersion. The de Broglie wavelength depends on velocity, right? So if you have a small halo with low velocity dispersion, the fringe size will be bigger. So that's what's going on, and a lot of groups have actually simulated this. And I should say, the group that really first realized and point out very explicitly, this is what you should have, was this one by scientists in Taiwan and also Tom Robbins. Okay. No, I'm running out of time, but let me also, I cannot resist actually pointing this out. And note the following irony, right? Fuzzy dark matter was originally introduced to suppress small-scale structure. So what this is showing you is, in fact, well, it actually produced small-scale structure. So there are many effects that one could talk about, and obviously we don't have time to talk about all of them. In this talk, I'm particularly focusing on wave interference, and I want to spend maybe 5 minutes talking about, actually there's something kind of non-trivial about this interference. It means actually your dark matter halo should have what we would call vortices. So I want to explain that to you. And then I want to spend 5 minutes telling you about direct detection. And another 5 minutes, we have 15 minutes. Another 5 minutes, probably a lot of you have questions. Okay, what are the current constraints, especially at the ultralight end? So I have a slide on that as well. So we'll see how far we can get. So let me tell you about vortices. Okay. At first sight, you vortices because in the fluid picture, once again, if it's a gradient flow, the curl of V is 0, so there should be no vorticity. Yeah. However, there is actually a loophole, and the loophole seems so innocuous that at first one might think this is actually. And the loophole is the following. If you think about the wave function, you split it into an amplitude and a phase. Well, there is at least one possible place where this splitting is basically ill-defined, and that's precisely where the amplitude is 0. Yeah? When the amplitude is 0, you cannot define the phase. And where's the amplitude 0? Well, it's where rho is 0. It means these are places where you have not just destructive interference, but a complete destructive interference. The density is actually 0, nothing. And let me point out, to have complete destructive interference is really a nonlinear effect, meaning it requires the fluctuations to be actually order 1 or larger. It can only happen in the late universe. Cannot happen in the early universe, because in the early universe, your scalar field is kind of homogeneous with 10 to the minus 5 fluctuations. Even if you interfere them, it cannot bring the density all the way to 0. It's impossible. So to have the possibility of this requires gravity to do the work, amplify the fluctuations to be order 1 or larger. And then you have this possibility. Now, this, again, at first sight seems such an academic question to ask. Isn't this very rare and so on? It turns out this is not very rare. That's basically the point. But let me tell you a little bit about how to think about these places now. So again, the picture is very simple. Interference produce a 0 amplitude, which means the wave function is 0, which means both is imaginary part and real parts are 0. And let's ask ourselves the following question, right? If I have 3 spatial dimensions, if I want to draw the set of points where the real part is 0, generically it will be some kind of surface. Think about contours. You are actually just asking where are the set of points where the real part take a certain value, namely 0. It will be from some kind of surface. And the imaginary part, likewise, it will be another surface. Where they cross is where you have complete destructive interference. And where they cross is going to be a line. And so generically, these places should form some kind of line. And I want to argue this line is some kind of vortex, is a line defect. This, by the way, is well known in the condensed matter literature. So the first point is the point I made already. You have a line defect. Well, the wave function now is very simple. So imagine this purple line is that line where rho is 0. The wave function vanishes, both real and imaginary parts. The phase of the wave function is ill-defined on that line, but it's well-defined away from that line. And if you ask, well, the wave function, the phase, how should it progress if you wrap around? Well, it must wrap around by basically integers of 2 pi for the wave function to be single value. And if you remember, the phase is precisely the velocity potential, and therefore if you integrate the velocity, integrate around this loop, no matter the size of this loop, you would get this integer winding. And so this is definitely some kind of vortex. And in fact, phrased as such, it sounds pretty dramatic because you have quantized circulation, right? This is what we would usually call circulation. You can say even more, actually. Because the wave function vanishes at a point, which I'm calling 0 here, imagine you just do a Taylor expansion. No? This would be the first term that show up in the Taylor expansion. It means a wave from basically this vortex line. The wave function scale like distance linearly with distance, which means the density scale like distance square. So the density profile is actually very characteristic. It has actually this prediction. You can convince yourself this circulation law also tells you the velocity should drop like 1 over r. In general, these line defects, they cannot just suddenly end in space. So they are like magnetic fields. So they have to somehow close upon themselves. So what you have is actually a vortex ring. So you should have a vortex ring like so. So let me show you some picture. You can find these things in simulation. And indeed, we look for these. You can find rings. I'm not showing the halo. The halo is is not shown, but the rings are highlighted. Of course, this is you have something that looks like this, but these rings are there. You can find them, and the way you find them is to look for this circulation. Because numerically, as you can expect, if you try to look for points where the density is 0, it's hopeless, because numerically, how are you ever sure this is truly 0? What you want to do is to look for this wrapping of the phase. And you can find these things. You can verify the density profile around these things, scale profile around these things, scale like distance square, the velocity profile, scale like 1 over distance. You can check all these things. These rings are very, because they actually behave like rings, vortex ring, just like in normal fluid. You might know, if you look at a picture of people do smoke, if you have a smoke ring like this, and if you have circulation that go this way, it turns out the ring cannot help but, as a whole, have a bulk motion going that way. And that bulk motion velocity scale like 1 over the size of the ring. Is very similar here, just like the smoke rings. And these vortices are very dynamic. Size expand, they can reconnect, they can shrink to 0 size and then disappear, and so on. So why do we care about these things? So number one, it turns out you can show these things are not rare at all. In fact, statistically, you expect 1 vortex ring per the body volume. Yeah? So it's not a rare thing, even though initially we thought this is just an academic exercise, but they are actually not rare. They have interesting motion. These vortices and the destructive interference pattern, they are transient phenomena, meaning they don't stay in place. They change. They change on what time scale? The time scale is, again, very easy. You take the de Broglie wavelength and divide by another power velocity. That is the de Broglie time. So they change on this time scale. If you have ultralight masses, the time scale can be long. It's like millions of years. Okay, so that's the fun stuff about vortices. Before I move on, yeah, John. The equation of motion actually is a little bit complex, meaning the way a ring moves depends actually on what other things are actually doing. So it's not a particle that you only care about what are the forces on that particle locally. So it's more like a non-local. It's a more non-local evolution. Yeah, it's a good question. Okay, so in the brief time remaining, let me not talk about this. So let me also not talk about this. You can see we introduce a method which is the wave analog of the classic Schwarzschild method for constructing halos like this. Let me at least tell you a little bit about experimental detection, and then let's talk about the current constraints from astrophysics. Okay. So we look for the axion or axion-like-particle. There are two couplings that are fairly natural to write down, and they are like this. The first coupling is the coupling of the axion to FF dual of E and M. This is basically E dot B of E and M. Okay, that's that. This little f is the axion decay constant, is that scale. So that is very natural. The other natural operator you write down is basically the coupling of the gradient of the axion to fermions. Psi here can be electrons, can be nucleons. Both of these operators are written down basically because they both have shift symmetry. If you shift phi by a constant, you get either total derivative or invariant action. Okay, so the fact that you can write these down fairly naturally suggests, and you do expect them to be present. They should come with this coupling, 1 over the axion decay constant, that kind of coupling. It tells you that, well, the way you look for these things is using the coupling to photons. For example, ADMX experiment try to look for the fact that if you have axion around and it's an oscillating scalar field, you turn on a strong magnetic field, which is this photon, you will produce an actual photon that you can try to detect. So that's the idea of these microwave cavity experiments. Okay. How about these? These is actually something else, which is kind of fun. This scalar, because we are moving, the solar system is actually moving through this axion bath. There is a gradient. This gradient is going to be there. There's some momentum if you want. And that gradient picks out a special direction, and turns out this coupling would cause the fermion spin to actually precess around that direction. So this coupling is proposed. In fact, that experiment, early version of that experiment has been carried out to look for these precession effects. So basically these effects. Now, what is the relevance of all these interference phenomenology that I just told you? So the relevance is the following. Traditionally, if you have a detector looking for axions, the traditional view is to think of the axion field as something like this. At that location of the detector, phi, as a function of time, is just some oscillating thing. Yeah, just like that. However, the fact that you have wave interference means, no, this is actually not what you should have at the location of the detector. This is what you should have. Yeah? So you would have these rapid oscillations on the time scale set by m, the mass of the axion. So that is there, which is basically this quantity. But you will have a longer time scale variation of the wave function because of this random phase wave interference. And so the envelope should fluctuate up and down on a time scale of basically the de Broglie time. And this time is long enough and not too long to be relevant for the actually experiment. Of the axion, they are best thought of as actually some kind of microwave background experiment or radio interferometry where you are going after a stochastic field with a predictable correlation functions. And as you can imagine, thinking about that way, it makes you think about how best to actually optimize your experiments. The existence of vortices is actually fun. It's interesting. Basically, it's telling you you should not just focus on the amplitude of the oscillations. In fact, you should think about the phase. The phase have interesting space-time structure. Okay, I think I'm out of time. I want to leave you at least with this slide. Let's quite wonder, what are the current constraints? So I try to list the current constraints here. And there are many, as you can see. I'll be happy to talk about any one of them individually, but I do have the following 3 messages in general, kind of overall for all of them. So these are my 3 messages, right? Number 1, you should take these constraints seriously, but as part of being serious, you should know their assumptions. That's important. For example, let me just give you an example. One of the first constraints that came out is a constraint from the Lyman forest. The fact that you have wave dark matter or fuzzy dark matter causes the power to be suppressed on small scale, and the forest is a good way to test that. If you look at in detail, these constraints, they come primarily from the highest redshift 5 or above. At those redshifts, you have to remember the fluctuation in the neutral hydrogen that you're observing reflect not just the dark matter fluctuation, but also fluctuation in the ionizing background and the thermal history, reionization history. And we are just at the beginning of exploring that, incorporating that into our constraints. So keep that in mind, right? So that's what I mean by know the assumption. So when you look at this constraint, you have to understand what is being assumed. Another point I want to make is understand the dynamics. I would say we are still in the early days of understanding precisely what wave dark matter or fuzzy dark matter actually predict, meaning the simulations are ongoing and getting better. For example, there is this nice constraint from the DES collaboration using basically abundance matching to constrain the subhalo mass function, looking at basically satellites of the Milky Way. We don't really have the subhalo mass function measured directly from these simulations. That really does not exist. And so this constraint has to rely on basically using the standard way of predicting subhalos using some kind of projector and so on, applied to fuzzy dark matter in order to get a constraint. So in other words, it is worth actually spending the time to just let's work out the dynamics, try to understand what the model actually predicts. So that's my number 2 point. And lastly, don't obsess about 10 to the minus 22. 10 to the minus 22 is the obvious target because it was proposed. It was proposed as the fuzzy dark matter value early on, about 20 years ago. On the other hand, at least for me, the main motivation for thinking about wave dark matter was actually because of this numerology. This numerology that you get the right, but that numerology argument uniquely pick out actually this number. That's a very large range. And I think it's helpful from that point of view. Just think of it as follows. The more we can push these constraints to higher masses, that's great. We can rule out actually more and more masses. And if we can actually push to very high masses, for example, here, this is the largest one, 10 to the minus 19. If we can do that, if we can even keep pushing, that's all the better, I would say. And let me just leave you with that. I'll be happy to discuss any of these. They are worth discussing and thinking about. I'm going to skip all the way to just the summary. This is my summary. The first point I want to leave you with is basically a very basic point. No? As long as you have dark matter particle lighter than 30 electron volts, the primary candidate is some sort of axion or axion-like-particle. You have wave phenomena, especially interference. There are lots of effects that one could look for, both astrophysical, if you are in the ultralight regime, or even relevant for direct detection, even if you are not in the ultralight regime. Thank you for your attention.
Thank you, Lam. So we have to clear the room in a couple of minutes, so it's time for one quick question, maybe.
Maybe at what mass would you say that you're not interested in this anymore, let's say?
Well, I would say I'm interested in all masses. So the traditional view is of 10 to the minus 22 is often motivated by what is known as the small-scale structure problem, right? As we know. On the other hand, we know it has been controversial whether the small-scale structure problem actually just have astrophysical solutions anyway, right? So I view it as one possible motivation, but for me, actually, the particle physics motivation is more appealing to me at some level. And so, given that fact, and given that it has such a wide range, let's use the best method we can to push on the band. And I think any improvement on the bound, I think, is interesting to me.
Since Lam's around this afternoon and tomorrow morning, so if you want to chat more with them, sign up. Schedule. So let's thank him again.